The whole demonstration includes a salt model, two complex models, a model to show our structural modeling workflow, a geomechanics model, a structural paleo-restoration model, and the last is a video to show our enormous modeling. First, let's start with a salt model. It's an artificial model built with complex salt structures and their geological context of a compressional basin. The area is 20 km by 19 km by 4 km. The blue areas are salt bed. As we can see, DepthInsight enables to build salt intruded into faults. Salt zones, and the diaper in overburden and horizons. With these 2D sections, it further illustrates the complexities of the structure. Next is a complex model with 90 faults, including complex strike slide and reverse faults. It's part of a compressional basin located at the northwest of China. The area is 58 km by 60 km by 4 km. From top to bottom, we can see the horizon structures. With these 2D sections, we can see DepthInsight enables to build a complex flower-shaped structure without any simplification. The third is a complex model with 280 faults, including complex sedimentary fault, strike slide and reverse fault. Also, an unconformity horizon at the model margin. It's 36 km by 44 km by 3.5 km, part of an extensional basin located at the northeast of China. It took us 5 days to build it. The model can be dynamically moved. It's easily and quickly moved through the model. With these 2D sections, we can see the complex fault truncations. Next, we are going to show the structural modeling workflow. The model we are going to use is 11 km by 12 km by 2.3 km. We can automatically separate and rename the data into individual faults that actually represent the geology. Generate fault surface, including fault boundaries automatically based upon the raw fault stick data. It usually takes 30 seconds. With these automatic functionalities, you can see DepthInsight is very easy to use and very fast. For example, with the automatic function of separating and renaming the data into individual faults, It can potentially be used to speed the preceding fault interpretation process, which can then be sent back to the original interpretation system. For this model, it really helps to resolve about 90% of the issues. Import horizon data. Generate a horizon surface. During the process of generating these surfaces, the software automatically ensures that the surface-to-fault intersections are watertight. We have just generated one horizon surface. We can examine the quality of our automatic process. As we can see, there is an issue. The two faults were incorrectly separated. We can edit them by selecting both individual faults to merge them into one. And now we will use a different methodology of automatically generating the new fault boundary for our merged fault. We next generate all of the full horizon surfaces. It usually takes 18 seconds. Generate 3 zones from our 4 surfaces. It usually takes 4 seconds. Close surfaces and horizon data to show zones. Use color to show zones. Scale Z direction from 1 to 5. We can also examine the structure from the 2D sections. Finally, we convert the proprietary grid to step-step grid for export. It usually takes 23 seconds. The export step-step grid can go to either Reservoir modeling software for subsequent property modeling and then Reservoir simulation, or it could just stay within the DepthInsight platform, where we can also do statistical-based property modeling, which could go directly to a third-party simulator, or to third-party petroleum system modeling, or other analysis or simulation. Next, is the geomechanical module. It's one of our specialized modules which go beyond the creation of the structural model. The geomechanical modeling using finite element stress analysis is 5 km by 3 km by 2.5 km, part of an extensional basin located at the northeast of China. It took 2 hours to build the structural model, 1 hour to build the geomechanics model. We need to specify some stress parameters, such as density, Young's modulus, Poisson's ratio, and others, and define or import certain parameters. Define base boundary conditions at each face of each layer, like external forces and/or constraints. On this face is shear stress. For this face is fixed constraints. Then we can calculate the stress field, like displacement, stress, and strain. It can be displayed in colors. Let's take displacement as an example. It can be displayed with the x component, y component, or z component. The calculation result can also be displayed in vectors, just like this stress model. We can see the variation of first principle stress, its direction and magnitude. This stress model can be applied to fault seal analysis and well trajectory designing. Next is another specialized module, structural Paleo-Restoration. It's a newly released version and the interface is still in Chinese. The previous version is kinematics based. The new one is finite element and geomechanics based. It took 2 days to achieve the full 3D restoration. As we can see, we can restore the geology from present time to Paleo time. And also from Paleo time to present time. We can also display it with displacement or strain or stress. The last is a video of enormous modeling. It's a real project. It's about 2,000 square kilometers, 1,600 faults, 9 horizons, 56,000 wells. We can cut any regional model and download the data. For this model, it has seismic data and well data. With combining this data, we can build a structural model. Then, upload the model into the database. The principle is that fragment the model and store it in the database with fields and tables. After uploading the model, to make it seamlessly merged into the master model, we should build a model next to it. The enormous modeling module facilitates distributed modeling, with multiple users working in individual subregions simultaneously. Just like the video shows, multi-users can download the right area. They can model on their own computer simultaneously and separately, and then they can update and seamlessly embed back into the master model. Any part of the master model could be downloaded for applications, like export stair-step grid and pipe grid. The principle for downloading models is that download fragments from database. Then the fragments can be merged as a 3D model for applications. It's very easy for us to open a 2D section at any location with any direction for quality control, or 2D maps. When we find a problem, we can just download the problem area and modify it. Then upload, have another 2D map for re-examination. For this model, the grid size is 20 meter by 20 meter, and it has 10 trillion cells.